Among the gas giants, Saturn, the second largest planet in the solar system after Jupiter, is notable for its majestic rings and expansive atmosphere. Saturn's size and appearance make it a prominent figure in the sky, especially its rings, which represent a colossal structure composed of ice and rock fragments orbiting the planet. These magnificent rings and Saturn's vast moons showcase the complexity and beauty of the solar system, making the planet a key focus for both scientific research and general curiosity. In ancient Mesopotamia, the Babylonians and Sumerians recognized Saturn as one of the significant planets visible to the naked eye in the sky. These civilizations carefully observed the movements and positions of planets, developing calendars and astrological systems. In these early astronomical systems, Saturn was known as Saturnu or Sataru. Greek astronomers also identified Saturn as one of the planets visible to the naked eye. In Greek astronomy, planets were associated with gods, and Saturn was linked to the agricultural god Kronos. Kronos was believed to be the father of the Titans and the leader of the gods. Greek astronomers and mathematicians began studying planetary orbits, although they were unaware of Saturn's rings. In the Islamic world, particularly during the Abbasid era, astronomy became an important scientific discipline. During this time, Persian and Greek astronomical knowledge was expanded and refined in the Arab world. Astronomers such as al-Biruni and Ibn al-Shatter closely observed the movements and positions of planets, gathering detailed information about Saturn's orbit and characteristics. In Europe, under the influence of scholastic thought, ancient Greek and Roman astronomical knowledge was re-examined. Astronomers continued to study planetary motions using Ptolemy's geocentric model. The discovery of Saturn can be traced back to ancient astronomers who observed it with the naked eye, but the existence of its rings was revealed later, when Galileo Galilei used telescope technology. In 1609, Galileo used his telescope to observe the night sky, and in 1610, he observed Saturn. During these observations, he noticed an unusual structure around the planet. However, since Galileo's telescope was not powerful enough to clearly display the rings, he misinterpreted them and described the planet as having handles. Although Galileo's observations revealed the existence of Saturn's rings, he was unable to gain precise knowledge about their details. The Cassini-Huygens mission, launched in the late 20th century, enabled a comprehensive study of Saturn. The Cassini spacecraft, part of a joint mission between NASA and the European Space Agency, was launched in 1997 and reached Saturn in 2004. Cassini was equipped to gather detailed data on the planet's atmosphere, rings, and moons. The mission provided in-depth insights into the structure and dynamics of Saturn's rings, revealing important information about their composition. Additionally, the Huygens probe landed on Saturn's moon Titan, collecting data about its surface, including the presence of methane lakes and its thick atmosphere. Cassini also provided valuable data on Enceladus, revealing its icy surface and subsurface oceans. The mission concluded in 2017 with a controlled descent into Saturn's atmosphere, offering critical data about the planet's atmosphere. Galileo's telescope was the first to reveal the existence of Saturn's rings, but the detailed understanding of their structure became possible thanks to the Cassini-Huygens mission. The data gathered by Cassini significantly expanded scientific knowledge of Saturn and its moons, unveiling the planet's complex nature. The origin of Saturn's name comes from Roman mythology. In Rome, Saturnus was known as the god of agriculture and time, associated with harvest and believed to hold power over abundance and the order of time. Saturn is the second largest planet in the solar system, notable for its immense size and unique gas giant structure. With a diameter of approximately 120,536 kilometers, Saturn is about 9.5 times the size of Earth. Its massive size has significant impacts on its internal structure and overall physical characteristics. Saturn's large volume results in its low density. In fact, Saturn's density is so low that if it were placed in a giant body of water, it would float. This low density is due to the planet being primarily composed of light elements, especially hydrogen and helium. Saturn's atmosphere consists of a deep layer of these gases, forming the majority of the planet's physical structure. The planet's physical properties and visual characteristics are shaped by its atmosphere, which is composed of hydrogen, helium, and trace amounts of methane, ammonia, water vapor, and other gases. Hydrogen makes up about 96% of the atmosphere, while helium accounts for about 3% to 4%. These two gases constitute the bulk of Saturn's mass and volume. The low density and lightness of these gases contribute to Saturn's overall low density. The upper layers of Saturn's atmosphere, especially the cloud layers, are made up of a combination of different gases and chemical compounds. These cloud layers form the colorful bands and clouds observed on the planet's surface. Methane, found particularly in the lower atmosphere, influences the purple and blue tones of the clouds. Ammonia is found in the upper cloud layers and creates white clouds in certain regions of the planet. Water vapor, present in various parts of the atmosphere, leads to the formation of water clouds. Saturn's atmosphere is highly dynamic and complex due to the planet's rapid rotation. This giant gas planet is one of the fastest rotating planets in the solar system. A full rotation of the planet takes only about 10.7 hours. This rapid rotation causes the formation of large-scale cyclones and anticyclones in its atmosphere. These atmospheric movements are particularly prominent in the equatorial region, leading to the formation of wide, colorful bands. The large-scale atmospheric motions on Saturn may also influence the appearance of the planet's rings. The fast rotation and large-scale air movements impact the dynamic structure of Saturn's atmosphere and weather patterns. The broad bands and cloud systems in the atmosphere are the result of the planet's atmospheric dynamics and contribute to Saturn's characteristic appearance. Saturn's atmosphere interacts with the planet's strong magnetic field, which affects the movement of gases in the atmosphere and shapes its dynamics. The influence of the magnetic field can affect air movements and cloud formations, playing a significant role in the planet's overall appearance and atmospheric conditions. One of the most intriguing and mysterious features of Saturn's atmosphere is the hexagonal storm observed at its poles. This phenomenon, particularly striking at the planet's north pole, has drawn significant attention from scientists. The hexagonal storm is a large weather system located at Saturn's north pole, characterized by wind currents arranged in a hexagonal shape. This hexagonal formation is about 30,000 kilometers wide and is distinctly visible at the planet's pole. Various theories have been proposed to explain how this unique structure forms. One theory suggests that the hexagonal shape results from differences in speed and direction in the atmospheric currents around the planet's pole. These atmospheric flows can organize into a hexagonal shape when moving at specific speeds and directions. The hexagonal storm is also supported by high-speed rotating atmospheric currents, contributing to the formation of this striking weather pattern at the polar region. This phenomenon highlights the complexity of the planet's climate and atmospheric dynamics. Saturn's mass is approximately 5.683 times 10 to the power of 26 kilograms, making it the second largest planet in the solar system, with Jupiter taking the top spot in terms of mass. Saturn's mass is about 95 times that of Earth. This massive size gives Saturn a strong gravitational field. The planet's volume is approximately 8.271 times 10 to the power of 14 cubic kilometers, indicating its large size with a diameter of around 120,536 kilometers. In comparison, Earth's volume is about 1.083 times 10 to the power of 12 cubic kilometers, meaning Saturn's volume is roughly 764 times that of Earth. This enormous volume shows that Saturn occupies a vast area and has a large internal structure. Saturn's magnetic field originates from the planet's core and greatly influences the planet's magnetic characteristics. Saturn's magnetic field originates from a layer of metallic hydrogen in the planet's interior. This layer consists of hydrogen and helium gases that have transformed into a metallic state due to the high pressure and temperature conditions surrounding the planet's core. The metallic hydrogen layer contributes to the generation of electric currents, which in turn produce the magnetic field. Saturn's magnetic field is further supported by the planet's rapid rotation, with a full rotation taking only about 10.7 hours. This fast spin influences the dynamic structure of the magnetic field. Saturn's magnetic field creates a vast magnetosphere around the planet, acting like a magnetic shield that protects its atmosphere from the effects of solar wind. The magnetic field is notably regular and symmetrical, meaning it is stronger near the planet's polar regions and weaker around the equator. Saturn's radiation belts are formed by high-energy particles trapped by the planet's magnetic field. These belts, primarily located in the equatorial region, consist of electrons and ions held in place by Saturn's magnetosphere. The belts are most prominent near the planet's magnetic poles and equatorial regions, representing areas where high-energy particles are concentrated within the magnetic field. Saturn's radiation belts reflect the dynamic effects of the magnetic field and interactions with solar winds. These belts provide important information about the characteristics of the space environment surrounding Saturn and its magnetic field. Additionally, they can have various effects on Saturn's moons and rings. For example, the influence of the radiation belts may cause dynamic changes and interactions in the planet's moons and rings. Moreover, the radiation belts offer insights into the behavior of high-energy particles interacting with Saturn's magnetic field. Solar winds, which are streams of high-energy particles emitted from the Sun, interact with the magnetic fields of planets. As part of the solar system, Saturn is exposed to these solar winds. When solar winds collide with Saturn's magnetosphere, they create changes in dynamics within the planet's magnetic field. This interaction influences the shape and structure of the magnetic field, and during these interactions, energetic particles move toward the planet's atmosphere. Saturn's magnetic field partially absorbs the effects of the solar winds, generating various dynamics within its magnetosphere. As the solar winds spread through Saturn's magnetosphere, they produce a shock wave and a cloud of plasma, impacting the planet's magnetic field. This interaction affects Saturn's radiation belts and auroras, shaping the dynamics of the surrounding space environment. Saturn's auroras, or polar lights, are the result of the interaction between the planet's magnetic field and solar winds. These auroras occur when high-energy particles strike the upper layers of the planet's atmosphere in the polar regions. As solar winds push electrons and other particles into Saturn's magnetic field, they are funneled toward the poles. When these particles collide with the atoms and molecules in the atmosphere, they produce glowing lights in various colors, forming the auroras observed in Saturn's polar regions. Saturn's auroras have been studied through space observations and missions, particularly by the Cassini-Huygens mission, which provided detailed data on the planet's magnetic field and auroras. The mission delivered critical insights into the structure and dynamics of Saturn's auroras. Auroras serve as a reflection of the interaction between the planet's magnetic field and solar winds and are essential for understanding Saturn's atmospheric and magnetic properties. Escape velocity is the minimum speed an object must achieve to break free from a planet's gravitational pull and escape into space. In other words, it is the speed required to overcome the planet's gravity completely. To understand this concept better, let's consider Saturn's escape velocity. Given Saturn's size, its gravitational force is quite strong. Saturn's mass is about 95 times that of Earth, leading to a significant gravitational pull. Escaping Saturn's gravity, therefore, requires a substantial speed. For an object to break free from Saturn's surface, it would need to reach a velocity of about 35.4 kilometers per second. This is much higher than the escape velocity on Earth, which is approximately 11.2 kilometers per second. Due to Saturn's massive size and strong gravitational influence, the required speed is far greater. This illustrates just how powerful Saturn's gravitational force is and how challenging it is to escape from the planet. Thus, a spacecraft or astronaut attempting to leave Saturn would need to exceed this speed. Saturn, one of the gas giants of our solar system, has a surface unlike that of any other planet. Saturn doesn't have a traditional solid surface like rocky planets. Instead, its structure as a gas giant means it is surrounded by a thick atmosphere primarily composed of hydrogen and helium. Therefore, there is no solid layer that can be called the surface of the planet. Instead, Saturn's interior consists of dense layers of gas and liquid. The planet's surface is defined by the clouds, storms, and various weather phenomena within its atmosphere. Saturn's atmosphere is arranged in layers, with each layer containing different gas components at various altitudes. These gases form clouds of different colors and densities depending on the temperature and pressure conditions. The lower layers of Saturn's atmosphere are composed of condensed hydrogen and helium gases. As these layers descend deeper into the planet, the gases become liquid. Near Saturn's surface, the gases form a dense layer of liquid metallic hydrogen. This liquid metallic hydrogen generates Saturn's strong magnetic field and contributes to the dynamic movements of its atmosphere. The internal structure of Saturn is layered, reflecting the planet's massive size and gas giant composition. At its center, there is likely a solid core that is about 10 to 20 times the size of Earth. This core is believed to be made of dense materials like iron, nickel, and silicates. Although the core makes up only a small fraction of Saturn's total mass, it has a significant influence on the planet's internal temperature and pressure conditions. Surrounding the core is a vast layer of liquid metallic hydrogen and helium. This liquid metallic hydrogen is a key component in generating the planet's strong magnetic field and contributing to its atmospheric dynamics. This layer makes up most of Saturn's internal structure. As it extends outward from the core, the liquid metallic hydrogen becomes less dense and merges with the planet's various atmospheric layers. Saturn's atmosphere includes a wide range of layers, from the gas clouds in the upper atmosphere to the deeper layers of liquid metallic hydrogen and helium. These layers are shaped by internal temperature variations, pressure conditions, and atmospheric dynamics. Scientists use data collected by orbiting satellites and space probes to better understand this complex structure. Saturn's temperatures vary greatly due to the planet's structural and atmospheric properties. In the planet's outer atmosphere, the temperature in the upper cloud layers is around -178 degrees Celsius -288 degrees Fahrenheit. These low temperatures are due to Saturn's distant location from the Sun and the limited energy transfer within its atmosphere. However, as one descends deeper into the atmosphere, temperatures increase significantly. In the regions near Saturn's interior, especially in the liquid metallic hydrogen layer, temperatures can reach up to 10,000 degrees Celsius (18,000 degrees Fahrenheit) due to the high pressure and temperature conditions near the core. This temperature increase involves the thermal energy of liquid metallic hydrogen and radioactive decay in the planet's core. Saturn's temperature profile leads to significant temperature variations within the planet's atmospheric depths. The low temperatures in the upper layers of the atmosphere explain the cold clouds and atmospheric phenomena observed at high altitudes. On the other hand, the high temperatures within the planet's interior can be attributed to its internal heat sources and thermal dynamics. The temperatures in Saturn's deep atmosphere are critical for understanding the planet's overall energy balance and thermal structure dynamics. This temperature data helps improve our understanding of Saturn's thermal and atmospheric structure and sheds light on the effects of the planet's gravity and atmospheric dynamics. Saturn is, on average, about 1.4 billion kilometers, 900 million miles, away from Earth. This distance can vary significantly depending on the changes in planetary orbits and their relative positions. Compared to Earth's orbit, Saturn's orbit around the Sun is much larger. Therefore, even when the planets are at their closest approach, the distance can decrease to around 1.2 billion kilometers, 750 million miles. At their farthest, the distance can increase to 1.6 billion kilometers, 1 billion miles. This vast distance creates technological and astronomical challenges for observing and exploring Saturn. Being so far away means that light and radio signals from Saturn take a long time to reach Earth. For example, a signal sent from Saturn to Earth, even at the speed of light, would take around 80 minutes to arrive. This time delay is an important factor when planning space missions and observations. Saturn's distance also tests the precision and technological capabilities of the telescopes and spacecraft used for its observation and exploration, yet it enables scientists to collect detailed data for in-depth study. Saturn's orbital period, the time it takes to complete one full revolution around the Sun, is approximately 29.5 Earth years. As the sixth planet in the solar system, Saturn's orbit is a wide elliptical path compared to the inner planets. This long orbital period is a result of its great distance from the Sun, which causes Saturn's orbital speed to be much slower than the inner planets. The extended duration of its orbital period highlights how slow and steady Saturn's motion around the Sun is. Additionally, Saturn's orbital period is influenced by factors such as its axial tilt and elliptical orbit shape. The planet's orbit is slightly elliptical, meaning Saturn's distance from the Sun changes over time throughout its orbit. The tilt and ellipticity of the orbit may lead to minor seasonal variations in Saturn's movement around the Sun, but the overall orbital period remains constant. This period not only reflects Saturn's great distance from the Sun but also demonstrates the regularity of its orbit. This long orbital period is essential for understanding Saturn's dynamics within the solar system. The planet's orbital movements, along with long-term astronomical observations and calculations, allow for a detailed study of its orbital characteristics and motions. A day on Saturn is the time it takes for the planet to complete one full rotation on its axis, which is about 10 hours and 33 minutes. This indicates that Saturn has a very rapid rotational speed. Despite its large size, Saturn's fast rotation results in much shorter days than those on Earth. The planet's rotation period affects its structural and atmospheric dynamics. Saturn's fast rotation causes a noticeable bulge around its equator, making the planet's equatorial diameter wider than its polar diameter. Additionally, this rapid rotation influences strong winds and dynamic weather patterns in Saturn's atmosphere. Saturn's rings are among the most impressive natural structures in the sky. These rings form a thin but wide disk surrounding the planet. But how did these rings form? How do their structures and dynamics work? Let's explore this mysterious feature in depth. Saturn's rings are primarily composed of ice and rock particles, varying in size from a few centimeters to several meters in diameter. These particles create gaps between the rings, enhancing their visibility. Several theories explain the formation of these rings, with the most widely accepted one suggesting that the rings formed from icy and rocky debris captured by Saturn's gravitational pull over time. These particles could have originated from the breakup of a moon or comet in Saturn's vicinity, which gradually organized into the ring system through prolonged dynamic interactions. Saturn's rings are much more pronounced and observable compared to the rings of other planets. This is due to several factors. Saturn's rings are significantly wider and denser than those of other planets, encircling the planet in a broad band, which enhances their visibility. Most of the particles in Saturn's rings consist of ice, which reflects sunlight, contributing to the ring's brightness and visibility. Additionally, the contrasting light and dark regions on the particles' surfaces make the rings more distinctly separated. Saturn's rings are constantly influenced by the planet's gravitational forces, which help maintain their regular and well-defined structure. Moreover, some of Saturn's small moons and internal dynamics create gaps between the rings, further contributing to their clear appearance. Saturn's rings are composed of many thin layers. These layers cause the rings to appear separated and result in various gaps. The rings of other planets are generally less layered and have simpler structures. Saturn's rings are located at varying distances from the planet's center, with this distance depending on the structure and width of the rings. The innermost ring, the D ring, is located approximately 66,000 kilometers from Saturn's surface. Beyond this, the distance increases as you move toward the planet's outer rings. Saturn's rings are typically divided into 7 main rings, each situated at different distances from the planet. For example, the C ring is located approximately 85,000 kilometers from the planet, the B ring is about 92,000 kilometers away, and the A ring is around 136,000 kilometers, 84,000 miles, from Saturn. The gaps between these rings are known to influence the dynamic structure and internal arrangement of the planet's ring system. These distances help us understand how far Saturn's rings are from the planet and reveal the organizational patterns within the rings. The distances of the rings play a crucial role in determining their shape and structure, as well as in comprehending the overall dynamic system of the planet. Saturn stands out among the gas giants in the solar system due to its size, rings, and unique features. Classified as a gas giant along with Jupiter, Uranus, and Neptune, Saturn is the second largest of these planets, following Jupiter. What distinguishes Saturn from the other gas giants is its more prominent and expansive rings, which are considered some of the most intricate and beautiful structures in the solar system. Studying the formation and structure of these rings provides deep insights into the planet's evolution and environmental dynamics. Saturn's size, mass, and gravitational influence play a key role in maintaining the balance of the solar system. Its orbit around the Sun can affect the orbits of other planets and the asteroid belt. Compared to the other gas giants, Saturn's atmospheric structure is also notable. Although Saturn shares a dense hydrogen and helium atmosphere with Jupiter, it differs with its unique weather phenomena, such as the hexagonal-shaped polar storm. In contrast, Uranus and Neptune, which are located farther from the Sun, have lower temperatures and appear bluish due to the dominance of methane in their atmospheres. Saturn's magnetic field, while not as strong as Jupiter's, is still quite impressive and significantly affects the movement of particles around the planet. These characteristics make Saturn a dynamic and essential planet for understanding the features of gas giants in the solar system. As a large gas giant, Saturn lacks a solid surface, making it inhospitable for life. Its atmosphere is mainly composed of hydrogen and helium, along with smaller amounts of gases like methane, ammonia, and water vapor, none of which provide the conditions needed for life to develop. Moreover, the extremely low temperatures on Saturn, averaging around -178 degrees Celsius, mean that no known form of life could survive. The planet's intense atmospheric pressure and violent storms further prevent the possibility of a stable environment for life. However, Saturn's potential for life may be more promising on its moons. Particularly, Enceladus, one of Saturn's largest moons, has drawn attention from scientists due to its subsurface oceans. The plumes of water vapor and ice particles erupting from Enceladus suggest the presence of liquid water beneath its surface. The existence of liquid water is one of the most fundamental requirements for life. Therefore, while the planet Saturn itself is not directly habitable, some of its moons, especially Enceladus, possess potential environments where life might exist. Saturn is one of the most fascinating planets in the solar system, with over 80 moons. These moons vary greatly in size and characteristics, with the smallest being only a few kilometers wide, while the largest moon, Titan, is even bigger than the planet Mercury. Among Saturn's moons, icy surfaces, subsurface oceans, and cratered terrains are prominent features. Enceladus, with its icy shell and plumes of water vapor, is a focal point in the search for potential life. Moons like Mimas, Rhea, and Dione, with their cratered surfaces, provide insights into the early history of the solar system. Saturn's largest moon, Titan, stands out with its distinct and fascinating features, differing from any other moon in the solar system. Titan is the only moon with a thick and dense atmosphere. Its atmosphere is primarily composed of nitrogen, similar to Earth's atmosphere, but it also contains abundant methane and hydrocarbons. This dense atmosphere continuously shrouds the surface, making it difficult to observe clearly. The methane cycle in the atmosphere behaves similarly to the water cycle on Earth, with methane clouds forming, falling as rain, and creating lakes on the surface. This makes Titan one of the few places beyond Earth with surface liquids. Titan's surface is particularly notable for the presence of liquid methane and ethane lakes, especially near the polar regions, where large methane lakes are found, forming a key part of Titan's climate cycle. These liquid hydrocarbons create an ongoing surface shaping process on the Moon. Titan also has geographical features such as craters, mountains, and cryovolcanoes. Due to the low surface temperatures, water exists in a solid state, as hard as rock. Titan's thick atmosphere and liquid methane on its surface make it an intriguing target for scientists investigating its potential habitability. Asteroid mining stands out as one of the most exciting and promising fields in space exploration. This innovative endeavor has the potential to reduce our planet's reliance on limited natural resources by utilizing extraterrestrial materials, and it offers the opportunity to open new doors in space exploration. The valuable metals and minerals contained in asteroids could make significant contributions to economic and industrial activities on Earth. However, to realize this potential, various technological, legal, and ethical challenges must be overcome. In this video, we will delve into the evolution of asteroid mining from the past to the present, examine current projects, and explore visions for the future. The idea of asteroid mining has traveled a long path from science fiction to scientific research. First proposed in the late 19th century with dreams of space exploration and utilization, this idea was prominently featured in the works of authors like Jules Verne. However, its conceptual foundations and scientific consideration had to wait until the mid-20th century. The 1950s and 1960s saw intense interest in space exploration and colonization alongside the space race. During this period, the potential resources of asteroids and other celestial bodies began to be explored. As NASA and the Soviet Union collected data on the Moon and other planets, scientists developed theories about the internal structures and compositions of asteroids. The 1970s and 1980s marked a time when the concept of asteroid mining was taken more seriously. During these years, the surface compositions of asteroids began to be analyzed, and potential mining methods were discussed. In the 1980s, NASA conducted the NEAR project to study asteroids and identify those suitable for mining. The early 21st century saw more concrete steps being taken toward asteroid mining. Significant advancements were made in this field through private companies, government-supported projects, and international collaborations. In the 2010s, pioneering companies like Planetary Resources and Deep Space Industries attracted attention with serious investments in asteroid mining projects. These companies emphasized that extracting valuable metals and resources like water from asteroids offers great opportunities for both the Earth's economy and space exploration. Today, asteroid mining is no longer just a science fiction concept but is seen as an achievable goal. With technological advancements, legal regulations, and international collaborations, efforts in this field have accelerated. This exciting and rapidly developing area will play a critical role in ensuring humanity's sustainable presence in space in the future. Asteroids are small, rocky celestial bodies generally found in the asteroid belt between Mars and Jupiter, with some also located in near-Earth orbits. They can vary in shape, size, and composition. Understanding the classification and composition of these celestial bodies is critical for the successful implementation of asteroid mining. Asteroids are generally classified into three main types. Carbonaceous asteroids are the most common type, comprising about 75% of all asteroids. They are dark in color due to their high carbon content. Their composition includes carbon, water-rich minerals, and clay. Rich in water and organic compounds, they are significant for water production in space and supporting space colonies. Additionally, these asteroids could serve as a fuel source for future space travels. These asteroids provide information about the chemical composition of the early solar system. Silicaceous asteroids make up about 17% of all asteroids. They are known for their bright and rocky nature. Their composition includes silicates such as olivine and pyroxene, as well as nickel-iron alloys. Due to their metal content, they are valuable for construction materials and technological applications. These asteroids may be differentiated into distinct layers of metal cores and silicate mantles through differentiation processes. Metallic asteroids are rarer, accounting for about 8% of the total asteroid population. They have a bright and metallic surface. Their composition includes some valuable metals like nickel, iron, and platinum. Due to their high-value metal content, they are the most sought-after asteroids. They have significant industrial and economic potential. Their surfaces are generally smooth and shiny. The most suitable types of asteroids for mining depend on the valuable resources they contain and the feasibility of extracting these resources. The surface properties of asteroids are crucial in determining mining methods. For instance, the presence of water ice in carbonaceous asteroids allows mining by heating to produce water vapor. For silicaceous and metallic asteroids, mechanical excavation and smelting techniques might be more appropriate. Space mining, aimed at extracting valuable minerals from asteroids, is an innovative and forward-looking field. This process entails significant technological and engineering challenges, and various techniques are being developed to overcome these difficulties. Key techniques include excavation, drilling, and smelting. The excavation technique involves mechanically removing minerals from the asteroid surface. This method is performed using various tools and machines depending on the asteroid's surface structure and composition. The excavation process typically uses mechanical arms, scoops, and excavators to dig through the loose soil and rocks on the asteroid's surface to extract minerals. This method is particularly effective for asteroids with loose surfaces and rocky structures. For example, Planetary Resources' Arcade series of vehicles use these mechanical excavation techniques to collect surface samples. The laser cutting method uses high-energy laser beams to vaporize or cut through the asteroid surface. This technique is highly effective for asteroids with hard rock structures and for precision work. Lasers offer precision and control while minimizing the release of pollutants. This method allows for the careful extraction of valuable minerals on the asteroid's surface. Drilling is used to access the internal structure of asteroids and extract deeper mineral deposits. It plays a crucial role in reaching subsurface mineral beds. Mechanical drilling employs drilling machines, drills, and bits to create holes in the asteroid surface and access the underlying minerals. This method is ideal for accessing subsurface mineral deposits. For example, Japan's Hayabusa 2 mission used a drilling device to collect samples from the Ryugu asteroid, drilling into the surface to retrieve valuable specimens from within. The thermal drilling method involves using high-temperature devices to melt or vaporize the asteroid surface. This technique is used on asteroids with hard and dense structures. High temperatures allow for the melting or vaporization of rocks, enabling access to deeper layers. Thermal drilling is particularly effective for extracting hard minerals. Melting is a technique that allows for the in-situ processing of materials rather than direct extraction. This method heats the materials on the asteroid surface, causing the minerals to separate and be collected. The in-situ resource utilization (ISRU) technique involves extracting water and other volatile substances from asteroids and making them usable in space. This technology melts or vaporizes materials on the asteroid surface to collect water ice, metal, and other valuable resources. ISRU technology is crucial for long-term space missions. For instance, NASA's ISRU projects are used to process water ice on the surfaces of the Moon and Mars, and these technologies can also be applied to asteroids. The mining techniques developed in the field of space mining enable the efficient extraction of valuable resources from asteroids. Excavation, drilling, and melting methods are selected and applied based on the types and structural properties of different asteroids. Asteroid mining is one of the most innovative and forward-looking fields of space exploration. However, since this process requires working in the challenging conditions of space, it demands numerous technological innovations and engineering solutions. Let's take a closer look at what these technologies are and how they work. First, asteroids need to be discovered and captured. This process begins with space telescopes and sensors. Projects like NASA's NEOWISE mission use infrared telescopes to discover and classify asteroids. These telescopes are vital for determining the orbits and compositions of asteroids. Additionally, remote sensing techniques such as spectral analysis and radar imaging can be used to gather detailed information about the surface properties of asteroids. Various mechanical systems have been developed to capture asteroids. Robotic spacecraft, as seen in NASA's Asteroid Redirect mission, use special gripping arms to capture asteroids and move them into a safe orbit. These systems form the first step in asteroid mining. Once an asteroid is captured, the mining process begins. At this stage, robotic mining vehicles come into play. Companies like Planetary Resources have developed autonomous robots to collect mineral samples from the surfaces of asteroids. These robots move across the asteroid surface, performing mining operations. Excavation and drilling systems also play a crucial role. Methods such as mechanical excavation, laser cutting, and drilling are used to extract minerals from the asteroid surface. In-situ resource utilization technologies have been developed to process the resources extracted from asteroids on-site. These technologies extract and process water and other volatile substances from asteroids, making them usable in space. Logistic and transportation technologies are required to transport the mined resources from asteroids to Earth or another destination. Recycling and storage modules allow for the temporary storage and processing of the minerals obtained from asteroids. For instance, the inflatable modules developed by Bigelow Aerospace can be used as storage and living spaces in space. Orbital propulsion systems play a critical role in transporting minerals obtained from asteroids. Various propulsion systems, such as chemical propulsion, ion propulsion, and solar sails, are used in this process. The Dawn spacecraft, using an ion propulsion system, demonstrated the effectiveness of this technology by studying the asteroids Vesta and Ceres. Energy production and storage in space are also important topics. Solar panels and nuclear power sources provide energy to mining equipment. NASA's space vehicles, like the Mars rovers, can conduct long-term missions using solar energy and radioisotope thermoelectric generators. In the processes of asteroid mining, data collection and management are also of vital importance. Artificial intelligence and autonomous systems optimize mining processes and perform autonomous operations. For example, NASA's Mars Curiosity rover has autonomous navigation and analysis capabilities. Communication and control systems also play a significant role. High-speed data transmission systems ensure continuous communication between Earth and spacecraft. Global communication networks like NASA's Deep Space Network enable constant communication with spacecraft, ensuring the effective use of these technologies. These advanced technologies help us make great strides in the field of asteroid mining. Thanks to these innovations, the processes of extracting valuable resources from asteroids and transporting these resources to Earth or other points in space are becoming more efficient and secure. Asteroid mining has the potential to revolutionize future space exploration and economic development. Significant progress has been made in asteroid mining through both government-supported projects and private company initiatives. NASA's OSIRIS-RX mission, launched in 2016, aimed to collect samples from the asteroid Bennu and return them to Earth. This mission successfully collected samples from Bennu's surface, and these samples were returned to Earth in September 2023. These samples provided valuable information about the composition of asteroids and offered important data for future mining operations. Japan's Hayabusa mission collected samples from the asteroid Itokawa and returned them to Earth in 2010. Following this success, the Hayabusa 2 mission collected larger and more diverse samples from the asteroid Ryugu, and these samples returned to Earth in December 2020. These missions provided important experiences and data for asteroid mining technologies. ESA's Hera mission aims to study the binary asteroid system Didymos, specifically investigating the smaller asteroid Didymon. This mission, working alongside NASA's DART mission, will be the first collision test aiming to alter an asteroid's orbit. The Hera mission will help us understand the structural properties and surface dynamics of asteroids. Planetary Resources is a company that develops commercial technologies for asteroid mining. The Arcad series space telescopes are designed to explore potential mining targets. The company aims to extract water and valuable metals from asteroids. However, financial difficulties have slowed down the projects. Transastra is another private company developing technologies for asteroid mining and fuel production in space. The Mini Bee and Queen Bee spacecraft aim to extract water ice from asteroids to produce fuel in space. These projects aim to establish a sustainable economy in space. These innovative technologies are paving the way for sustainable economic activities in space. The universe possesses a grandeur that captivates our eyes and is truly worthy of exploration. Galaxies, as vast collections of stars and planets, are among the most striking elements of this cosmic landscape. However, the stars within galaxies do not exist in isolation. Many of them interact with each other, moving in pairs. Binary star systems are fundamental building blocks of these enormous stellar assemblies. A binary star system consists of two stars that orbit a common center of mass, held together by their mutual gravitational pull. These systems are recognized as structures where stars are not solitary but interact with one another. Throughout much of the universe, such systems are prevalent, and it is believed that most stars move in conjunction with one or more companions. Understanding binary star systems is crucial for our comprehension of stellar evolution and galactic dynamics. The formation of these systems typically occurs through two main processes. The first involves co-orbiting pairs, where two stars originate from the same molecular cloud and evolve together within it. These pairs are often found in young star clusters and initially have a close proximity. In this scenario, the stars share a common origin and interact closely with each other. The second formation process involves pairs that come together later. In these cases, two independent stars, when sufficiently close to each other, form a binary star system through gravitational attraction. This process is characterized by changes in the star's orbits over time. Such pairs often form in older star systems or as a result of interactions with planetary systems. The dynamic structures of binary star systems are highly complex. The stars revolve around a common center of mass, which represents the point of mutual gravitational influence between them. The distance in orbit between the stars vary depending on the system's type and the star's masses. The orbits can be elliptical, circular, or intricate. Over time, the orbits may change, a process influenced by orbital eccentricity and shifts in the orbital axis. In binary star systems, it is possible for one star to transfer matter to the other. This process, known as binary star evolution, significantly impacts the evolutionary stages of the stars involved. The interactions between the two stars in such systems can be highly complex and dynamic. These interactions play a crucial role in determining the orbits of the stars and the overall behavior of the system. As the two stars orbit each other under the influence of gravity, several key aspects of their interaction emerge. The orbits in binary star systems are shaped by the masses of the stars, their velocities, and the distance between them. The interaction between the stars can lead to various cosmic phenomena. For example, the transfer of matter from one star to another can alter the mass of the receiving star, thereby affecting its evolutionary process. The gravitational pull between the stars in binary systems can trigger various interactions, influencing the dynamic properties of the system as they orbit their common center of mass. This gravitational interaction can cause changes and perturbations in the star's orbits, leading to irregularities and shifts over time. Additionally, the interactions between the stars in such systems can affect the system's total energy and angular momentum. Binary star systems are among the most prevalent cosmic structures in the universe. The majority of stars are not solitary but exist in pairs or within larger systems. Astronomical observations and research have revealed the widespread occurrence of binary star systems in galaxies and star clusters. Various observations and studies have shown that approximately 50% to 75% of stars in galaxies are found in binary star systems. This estimate has been determined not only through direct observations of stars but also through gravitational interactions and other astronomical measurements. The proportion of binary star systems may be higher, particularly in young star clusters. This is often explained by the fact that stars are born from the same molecular cloud and move together. Binary star systems can exist in various forms, each with its own unique characteristics and interactions. The primary types of star systems include physical binaries, optical binaries, and visual binaries. These types are important for understanding the interactions and observations of stars. Physical binaries are systems where two stars orbit a common center of mass under the influence of gravity. These pairs are truly interacting with each other, and their orbits can be observed. Optical binaries, on the other hand, are stars that appear close to each other in the sky but are not actually interacting physically. They only seem adjacent due to the line of sight. Visual binaries are stars that appear close together during observations, but in reality, they are not physically interacting and are located at different distances. Sirius, known as the brightest star in the night sky, is a binary star system. Sirius A, the primary star, dominates the system and orbits together with a white dwarf star called Sirius B. Sirius B orbits the larger Sirius star approximately every 50 years. Located about 8.6 light-years from Earth, Sirius is a prominent and easily observable star in the sky. This binary system provides valuable insights into stellar evolution and cosmic interactions and holds significant importance in astronomical observations. Alpha Centauri, one of the closest star systems to Earth, consists of 3 stars. These stars are Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Alpha Centauri A and B form a binary star system, orbiting each other under the influence of gravity, while Proxima Centauri is approximately 0.2 light-years away from this system. Proxima Centauri is the closest star to the Alpha Centauri system, and this system is considered a valuable laboratory for studying stellar evolution and galactic dynamics. The Alpha Centauri system is about 4.37 light-years away from Earth. Betelgeuse, located in the Orion constellation, is a giant red supergiant star and one of the brightest stars in the sky. It is approximately 700 light-years away, making it a distant star. Some observations suggest that Betelgeuse might be part of a binary star system, but debates about its physical interactions and binary nature persist. Its large and expansive structure makes it one of the most massive stars in the universe and serves as an important example for understanding stellar evolution and cosmic processes like supernova explosions. Castor is an impressive star system in the Gemini constellation and is actually a binary star system composed of 4 stars. It consists of 2 physical binary star systems, Castor A and Castor B, each of which is a binary star system in itself. Castor is located approximately 51 light-years from Earth, and its complex structure plays a significant role in understanding the interactions between stars. Despite appearing close together in the sky, the binary pairs within Castor exhibit intricate orbital dynamics. Mizar, located in the Ursa Major constellation, is a well-known star system and is recognized as a notable binary star in the sky. Mizar is actually a binary star system composed of 2 physical stars, Mizar A and Mizar B. Additionally, there is another star, Alcor, which appears optically close to Mizar, creating an optical binary system with Mizar. Mizar is located approximately 78 light-years from Earth, and this star system holds significant importance in the sky due to both its optical and physical interactions. The complex structure of Mizar makes it an intriguing and valuable example for astronomical observations. Spectroscopic binaries are binary star systems where the presence and interactions of the stars are detected and studied using telescopic spectrum analysis. In these systems, changes in the star's spectra are used to understand the presence and orbit of the binary pair. As stars orbit each other, their spectra show a change known as Doppler shift, which is analyzed to determine the star's velocities and movements. Spectroscopic binaries often provide crucial information for measuring the physical interactions and masses of stars, making them valuable tools for studying stellar evolution and dynamics. In binary star systems, stars are typically categorized into 2 main groups: hot companions and cool companions. Hot companions are stars with high surface temperatures, usually appearing blue or white. These stars are often young, high energy, and emit intense radiation. Cool companions, on the other hand, have lower surface temperatures and can appear red or orange. These stars are generally older, lower energy, and usually have lower masses. The temperature difference between hot and cool companions provides important insights into the star's evolutionary stages, masses, and interactions within the system. This difference is thoroughly examined through spectroscopic analysis and observations, playing a critical role in understanding the dynamics of binary star systems.